something we've covered recently, something you're struggling with. This is nominally a statics and mechanics of materials help session, but we've covered a lot of that, but we can recover some more things. Something that you would like to, we can do some statistics if you want to. I don't like it, but you can. There were other examples I had prepared. We could do that. That's the homework due on Tuesday. Stress concentration things. Yes. We could do a problem that involves stress concentration. Let's do one of those. Let's do one of those.
I really just need more practice with anything. So.
Okay. Well, so let's do a practice with anything and include stress concentration. Sounds like a plan. And we will have more things along those lines as well as the semester proceeds. Do more Brookings stuff. That's in chapter 6. Let's look for something either in chapter 5 or chapter 3, because chapter 3 is actually where stress concentration was introduced. But this right here, let's see. Right, so I wish they had. They recycle problems throughout the book, but that's. See, these are failure theories. We're just going to start with those soon, so we don't need to do those right there. I think we're going to have to invent a problem, but I really like when we do have an answer. I'm not good at reading quickly, but I was thinking about, let's see, 36. 5 of the forces right here. The problem illustrates that the safety of factor machine element on a particular point of analysis. Here you are to compare the factor of safety based upon the distortion energy theory. No, okay, I'm sorry. So it doesn't have that. Okay, so let me think. Let's find one. Plot on the loci. These are all things that are related. So let's go back to chapter 3. Sorry for the hemming and hawing. Let's see, what section is stress concentration right there? It's in 13, which is kind of after that, and we'll come in before pressure vessels. So when it comes to problems, they're roughly in the right place. We got that guy here, so it should be using. This makes for good video. Using allowable things to determine the power it can handle. Okay, so cantilever right here. This is really the problem here, right? This is that problem. All right, we're gonna make one up. All right, we'll do. Everybody needs more screwy shaft work. Let's do this problem right here. This is the one that's assigned for the recoup. Already made a video for it. Let's do this one right here. This is a ridiculous problem, by the way. The results of this problem are like this shaft was really poorly designed. So we're going to make it even worse. We're going to make it because we're going to put stress concentration in it. Let's say that everywhere where it's making a transition between a shaft and a thingy, it has a fillet of, I don't know, I'll say 1/8 of an inch, 1/16. Let's say there's fillets everywhere as 1/16. Usually it'll say on things, maybe, okay, 1/16 of an inch. So we're going to go 1/16 of an inch. All right. Is this is a ridiculous problem, so I'm not going to assign this problem or ask it on an exam. So that's a good enough reason to do it. So this is problem 383 out of the book. And I'm not going to try to draw it perfectly, just enough. Probably nicer than some other students, but not as nice as other students could do. I was just having this conversation with Dr. Asaki. We talk a lot. About work, student work, and about the best way to teach things. And I was describing that some students, and inexplicably, will never ever follow instructions. They just won't. And I gotta wonder why. Right? Sometimes like I would like you to do it this way, and sometimes I wonder, it's like, do they think I'm full of it? Do they think I am just randomly asking them to do the thing this way? Do they think I'm not, like, well, you were asking for it that way, but that's not the way I like to do things, so I'm not going to do it that way. It's just it's almost a philosophical question on my part, like, why? And I was like, well, maybe if we got all of the instructors in engineering to require the same amount, like, some people's work, and I don't know if either of you, I haven't memorized your work, just, they write so poorly and so scatterbrainedly, they won't write down anything that you ask them to, won't draw a free-body diagram, won't write the equations they're using. It's just random stuff. You look at that and you go, how is this person going to function? And if anyone ever asks, hey, can you, try to calculate this out, and show me your work. And when an employer sees what they've written down, well, they go like, I'm never trusting that person with anything, ever. I had young engineers who worked for me. I mentored them, and that wouldn't be acceptable to me. I just wouldn't accept it. Like, no, yeah, do that again. Like, sometimes I have to show people's work to my boss, and I can't show that to my boss because my boss would be like, who did this? Don't have them do any more work on my projects for my company anymore. And then you're like, oh, I'm not saying that actually ever happened, but it would. So you guys, not only are we learning things and learning how to solve problems, but we also have a certain amount of training. Like, welcome to the industry. This is how we do things, and we want you to succeed. So you are now a part of this club. You will now do the things we're asking you to do. But if we can maybe get all the professors, everybody has to use engineering paper. Let's just all decide. We're all going to do it every single time. And I will give you a 0 every time you turn in something that's just unacceptably messy. That doesn't require that. And I don't want to be the only person, and sometimes I feel that way, that's, asking these things. I don't want to be a tyrant. All right, so D is 1.25 inches diameter. DA is, where'd you go, DA? 20. You can't see the thing. I'm going to put them next to each other. Inches DV. And I think this right here is an acceptable enough amount of, I'm not a great draftsman here, but I think that's an acceptable thing. And doing too much more sloppier than this isn't acceptable. So somewhere near this, do better than me. How about that? And then they gave us FA is 300 pounds force. So here is a typical 3D shaft problem. And then we also decided that the R's are going to be 1/16 of an inch. So we can kind of build off of that. So we have to go through this whole process, and there's a certain amount of systematicness that makes it feel good to organize your brain by organizing your work. And so we start out with some geometry. We don't need the area, but we do need the moment of inertia, or we will. Just a good place to start. And we'll need the polar moment of inertia, which is just 2 times the area moment of inertia. So that's 1.25. So we want. I don't have to put 1.25 in there. 4 pi times 4 by 10. I think I got it right, but I don't know. I'll get the extra thing there. And so 2 times that, 3.835. Now we're going to do the loads. And by loads, one of the first things I need is they didn't give me this. So we got to get that. Best way, I don't know. I was about to say something. I go back and forth. I could break these into components right away. Sometimes that's what I do. Maybe that's what I'll do here. It's a good idea. Take FAX is going to be the 300 times, oh not X, sorry, Y. Right, I'm going to go that component first. Kind of makes sense. So that's going to be cosine, and that's 20 degrees. And so we'll put that one there. And so notably, that's going to be this one right here, the FAY. We're also going to have an FAZ. So I'll write that. So 320 cosine. And that 20 degrees is the most common pressure angle. So there's actually a real thing. It's not just a thing they made up, although they did, with the dimensions they gave, as I recall, were ridiculous with these loads. And this is only 102.6 pounds. We also have this coming this way, which is going to be the FBZ. Here's the FBY. Not to be confused with the FBI. Different thing. FBD, which is an important thing. And I just did the wrong coordinate axes. This is going to be actually the YZ. Ooh, stomach is going a little weird there. That ain't good. I could put in reaction forces here just to make it complete. R, Y, R, Z. But those are just a representation of the reaction forces here and here. They're in the way of each other actually here, so they're just a space holder, just because we know there are reactions there, but there's 2 of them, so they would be all messed up if you try to use right here. But what we really care about is some of the moments about the x-axis. And we made ourselves a little bit of easier by breaking this up, because we could see only this one creates any moment. And so that's going to be, and he's clockwise. So it'd be F, I don't know why I decided to go symbols. So that's going to be times dA over 2. It's going to be the moment arm right here. It's passing, there's passing here. And then this one is the one that we want to know. That's going to be positive FBZ. And that's moment arm right there. It's going to be dB divided by 2. You can see actually you get rid of those 2's if you want to. So really what you're saying is that BZ is going to be equal to FAY dA over dB, or 281.9 times 20 divided by 8. So that that would be more now, wouldn't it? Did you ever see the movie about the women's baseball league called A League of Their Own? That's a good one. John Lovitz plays a very small role where he recruits them, and they're in the barn, and he tells Gina Davis's character how much they'll be making, and Rory Petty says, "We only make this at the whatever," and he goes, "Well, that would be more now, wouldn't it?" Love that line. I use it all the time. Well, that would be more now, wouldn't it? Your favorite sports movie? Yeah, I don't know if that's my favorite sports movie. What is it? Ooh. Well, Caddyshack count? Not really a sports movie. All right, so to get FBY, we need to use a trigonometric function. I think we want to divide. It's rise over run. No, so we multiply, right, by the tangent of the angle. Do we have agreement? Right. We need this one. We know it's 20 degrees. So we need to rise. So we need to multiply the run by the tangent to get the rise. This is rise over run. I don't like math. That's not true, though. Tangent of 20 degrees, am I off the page yet? No. Equals, so it's 20 tangent times, we get 256.5 pounds force. All right. While we're here and doing this, it'd be smart to get the torque. But we can't get it from here because the torque is hidden inside. We got to split it apart. So either way, we either go for this, we either go this gear by itself and find the torque in there, or we go this gear by itself and find the torque in there. So because the bigger one is easier to draw from this view, we'll do that. So now we just have this alone, and now we've exposed the internal torque that's right there. And that torque inside, and from this point of view, will be in that direction. And I didn't leave enough room to make myself have reactions, but once again, I figured I'd put them in there just for completeness to make it a real FBD. Doing the same sum of the moments about the X, but this time we have a torque that's going to be inside there. It's going counterclockwise, so I made that one first and made positive. Minus my FAY times DA over 2. I need that 2. So the torque is going to be the 281.9 from up here times my diameter, which is 20 divided by 2. And so I think I can do that in my head, almost 2,819 inch-pounds force. I don't like doing that pound force thing, but now that I'm teaching thermo pound force, I gotta do the pounds force and pounds mass. Oh, I don't like that. What's thermo doing? You know, I'm on record right here. I'm being recorded, right? So I don't want to say bad things about my students. I care about my students, and I want to see them succeed. But I wish they would just have a little bit more of a, I don't know, fun attitude. I think they're in a dark place. Brings me down. Now we're going to do, I'm going to try to squeeze it in. Probably not smart to squeeze it in, but I'm going to do it anyway. Squeeze in the FBD / I'll do the work on the next page, I guess. It really is worth just going to the next page, but there's a big blank space right here. I just couldn't stop myself. So maybe I should be a better role model. Charles Barkley said famously that I am not a role model. I'm a basketball player. Then he became an old model. Come on, Chuck. I like Charles. He's had a good career thus far as a commentator. Okay, so this is the X direction. And here's the Y direction, and then here's the Z direction in our two things. If you're not feeling comfortable with that, tell me if you know the drawing of this thing. Actually, this isn't too hard. It's really sort of breaking down and putting the forces in the correct location. That's probably the only thing that really gets people messed up. So actually, so it might have helped for me to have broken it down this way right here. So when you go, so sometimes coming from this to these can be a little bit of trouble. So if that's the case, just remember a nicely drawn thing can help you say, all right, here is the Y component, and it's going to be positive Y when I'm looking from it from that point of view. Right? When I'm creepy eye this way right here, I can see it coming upwards onto here. And that's going to be F-A-Y. But then when you see this guy, you could see the Y component coming downwards. You could actually see it over here, and you could see, and I'm going to draw it on top of the thing because it's right there. So here's the F. They decided to go B. I think it's a little weird in this problem. They went O-A-C-B. That messes me up. O-A-C-B. Weirdos. And this is. Was that? Is that true? I think it's actually did numbered letter B. Did I number it the wrong thing? No, yeah, see. It says that's C and that's B, so that's B. Yeah.
I numbered it wrong.
Yeah, no, it's okay. No, I'm just not trying to argue. I'm just. I feel though I want to be argumentative. That's not true. This reaction, by the way, drawing the reactions can be a little bit challenging when you have. I think of this as the seesaw configuration. It's kind of like hard to figure. A lot of times they'll be in the same direction. It's easy to figure out what the reactions are. This one could you want to make it kind of up, but that's also going up. This one for sure. Well, I don't know. I think this one is going to be this direction right there. Let's make them both in the Y direction positive. It's just a little bit of an obstacle that happens every now and then, and this is one of those cases where we have to. We don't know for sure which direction these reactions are going to go because they're dependent on the magnitudes of these forces and these distances. This one has a chance of having to be downwards because this one could be so large. It has to keep the thing up. But, same thing over here with finding the loads. Let's take a look at this point A and what that looks like from the downward facing direction. I've put positive Z is that way, drawn that, we're looking up down that way, so we're looking down that way, not to the way. And what we will see here is this component, the small component, going in a negative Z direction. That way right there. So that's F-A-Z. And then we will also, here in that field, we'll see B, we'll see the main one going in the positive Z direction right down there. So there's probably a bunch of different ways that we could try to think our way through, and maybe that would work for various for different people to try to reason out how to place these forces on there. I guess if I'm going to be consistent with what I just said a couple of seconds ago, which is rare, but I'll do it anyway. That's supposed to be R, sorry. It's a reaction. I like using this. Over the years, I've come up with various things. I'm like, I think this is a nice way to approach calling forces that are applied to things and reactions that are the result of those forces being applied. So F's and R's. And so now I'm going to transition away from the clipboard because that doesn't help me much. We will do some statics. Maybe I'll write out the numbers in here just to make it a little easier for myself. There's 16, 14, and 9. 16, 14, and 9. Starting with this one, sum of the moments about O is equal to 0. But please ask questions at any point, because I know that I've been talking a lot. I want to be more interactive. So, how'd you know to do that? Or, I'm feeling comfortable with this already. Or, your wife looked really nice when she was pointing at you. Look how young she was. She doesn't look a day older right now, by the way. We have a painting of her that's in the attic, and it's aging. Do we know, are you guys familiar with what I'm referring to? The painting of Dorian Gray, or the portrait of Dorian Gray, an old book by Oscar Wilde, where there's this guy named Dorian Gray, right? And he was also kind of a naughty boy in England, and whatever. But the 1920s, I'm sorry, when Oscar Wilde was anyway. He didn't get older, but all the debauchery and all the bad things that he ever did were reflected upon in his portrait and his painting. Painting was sort of magic, and would change, and he wouldn't age, but his portrait did age. It's a famous book, Portrait of Dorian Gray. So I was making a reference, a literary reference. Mrs. Wright would be so proud. The English teacher, very happy with that. Okay, that was useful. Let's start here. This is going to go counterclockwise, so I don't know if I have to. Yeah, we know this value. Let's use values instead of symbols, and then do values shorter anyway. So I'm looking at my topic right here. And FAY is 281.9, and the moment arm is 16, and then this is an unknown, sort of the point of the whole thing. And they go RCY, and that's going to be 16 plus 14. Please tell me that's 30. Thank you. And then lastly, we're going to go negative. Don't go negative, go positive. And FBY is our 256 up here. 256.5. And now it's going to be 39, because we just had 30. We're going to add 9 to it, 39. Equals 0. Oh, I really hate when people write this equals that. No, I can get over it. Can I get over it? No, probably not. You don't see over it. All right, and then 256.5 times 39. Boom. But that's going to be subtracted. I think I got it right. Okay, I think RCY, if I'm correct, is going to be positive 183.1. I think I might have screwed it up. There's a chance I screwed it up, so I had to double, triple check, right? That I had pretty good confidence that this one was going to be up. It's this one that I think might be the opposite direction. So we do the sum of the forces in the y direction equals 0. And then say that ROY, which is Roy, I like Roy, and then FAY, which is the 281.9, plus my reaction RCY, which we just found out was 183.1, and then minus my R-B-Y. Ribby? I try to pronounce all these things. If you've been in the military, they like to pronounce acronyms. There's all kinds of things. They're always pronouncing acronyms. Can I tell this story about the gold that turned into the LEAD program? So they, at the Coast Guard Academy, they had this thing, they go to the gold team. Right, so Roy turns out to be negative, so he was backwards. So the Guide to Officer Leadership Development, the gold team, was a program that was obviously trying to make leaders into these young people. And it wasn't working, apparently. They were upset about it, so they decided to start a whole new thing, and they came up with the whole system, and they decided that we're going to have a meeting with the faculty as individual departments to introduce the new program. And they unveiled it, and it was the LEAD program. Leadership, Empathy, Assessment, and Decision, or something like that. I don't know. I'm coming up with words.
I think I know where this is going.
I raised my hand and pointed out that they just turned the gold into lead. Called reverse alchemy. No, it wasn't popular.
That's why you started doodling and reading this thing.
Not exactly. I had been doodling all along, but I did break my rule of never speaking in a meeting. I actually would write at the top of the page of the doodle often, keep your mouth shut. I'm like, yeah, it's good. This is actually mentoring 101 here. I'm trying to be helpful for you. It's a good idea. Just if you can make it through a meeting with us, say anything. It will probably help you. If you can just answer with single words. Yes. Okay. Maybe 2 words. Will do. There you go. The meeting will go so much better. So here's FAZ. Yeah, I don't know if I was helpful at all to you in your career just now. Would have helped mine. Times 16. Right, so we're going counterclockwise for this 16. And this one is the one we're trying to find. And this one is clockwise. RCZ. And then 2 is times 30, because that's 16 plus 14. Now, I'm kind of let down that the story didn't go as well as I'd hoped. All right. RBZ. This is probably going to be the opposite direction, I think. I can already tell. This one, RBZ, was the 704.8. And it goes times to 39, right? So 102.6 times 16. And, okay, we can subtract out 704.8 times 39. Boom. Yes. And because this is jumping over the other side, we're going to find that RCZ is going to be a negative value again. So we chose poorly. Indiana Jones reference. The Last Crusade. When the knight tells him to choose which holy grail is, and the guy dies. You chose poorly.
That was a good scene.
It's a good scene. That was a good movie.
That was a good movie.
All the other ones that follow,
Yeah.
it's like, wow, you should have stopped. So let's go ROZ minus, I'm just using the,
Can you repeat that?
excuse me? Sorry. And so this is up, our AZ is 102.6. This was drawn in the wrong direction, so you got to be careful here. Right there, we could go plus and then go minus, because that's what we just found, right? Technically true, right? That positive is because the arrow was in the positive direction, but the value that we got was negative. So then I don't have to update this right here, but we could just write it down. Foremost. I don't know, could we say we were amongst friends? I don't know. We could say that we're people who respect each other. Friends is a high bar. And you don't want to just toss that around willy-nilly. You don't even want to say the word willy-nilly, really. I'll try to avoid ever saying that. I just did. The 102.6 minus that minus, boom, willy-nilly. And then we had 704.8, we're adding to it. But we get a negative number, which turns out it jumps over the other side, so we get a positive number. So that we did choose this one correctly. You chose wisely. Which is 259.3 pounds. How am I doing my time? Probably terrible. Yeah, sure. Of course. But this actually is the hard part, right? This is the time-consuming part. Truthfully. The next portion of this, we don't want to go too fast over it because people have still struggled with this. I watch people with certain aspects, and I go, well, that's not good. All right, please don't do that. All right, so first off, this is a different one than we've done up till now because we usually have simply supported where those supports are at the end. But now we have a cantilever thing coming up here. What we do know about this situation is that this bearing can't support a moment. And this bearing can't support a moment, but it doesn't influence any kind of moment. So there can be a moment there inside the shaft. Here we know that the end of the shaft, there can't be a moment right here. So what we previously said is that the bearing can't support a moment, but that is while that remains to be true, but it's not stopping stopping the shaft from having a moment there. What we do know is there can't be a moment here, and there can't be a moment here. So just remember that when we get down to here. I saw a lot of people that would end their diagram coming up to a spot right there. It has to return back to here. And that will actually be a check if we wanted to on our reactions. But let's come along here and say that we're going to have ROY, which is coming down. So we've drawn it wrong right here. So maybe I'll concede. I'll do a cross out there. That's information to me that I originally drew it wrong. All right? So I don't need to erase it, but I'm telling myself, it's actually going the other direction. So it's going to be in the negative y here of being 208. I'm just going to pick sort of a kind of a line right there. And I might be able to write negative 208.5. And now we're going to go upwards here for FAY, which was 281.9. So those are really close to each other. 281.9. So we're going to subtract out 208 from 281.9. Subtract it out. We get there's a positive value, but it's pretty small. So relatively, I'll make it a thin looking thing and make it 73.4. And we lost a sig fig along the way because I'd only written down 4 for my in-between stuff. We'll probably be okay, but if we get different from like some other answer, that might be the cause. The RCY kept going upwards, right? This one was correct, and the RCY was 183.1. So we're going to add that to 183.1. Add that to, and we should get this right here. So I've added 183.1 and I've added it to 73.4. We should get 256.5, which should equal FBY. You agree with that? You see the logic behind this? Okay. And is that true? Where's FBY? There it is right there. 256.5. We got it. All right, and now let's go ahead and do this. I don't have my straight edge with me. But this is negative, therefore it's going to be going downwards. And if we want that value, it's 208.5 times 16. 208.5, 16 times. So we'll get 3,336. Let me label these over here. So this is going to be pounds force. This is going to be inch pounds force. And now we don't have to label this thing with it. So this is going to make this less negative by how much? Well, we can go 14 times 73.4. 14, 73.4. Boom. So we're going to get, this, by the way, this should be negative. Strictly speaking, that's negative. We add, or like maybe subtract, I guess. And of course, this represents the slope, by the way, this value. So we can make the slope not a whole lot. Does that make sense? So the value I got was 2,812. And it's still negative, so cool. Now, this one goes to 0. It has to be 0 right here at the end. Because here at the end of the gear, right, there's nothing that's going to make a moment. So, but let's check it. That means that 256.5 times 9 should equal this. And it does. No, it doesn't. I messed up somewhere. Did I use 14 here? Let me try this again. All right. So I messed something up. Let me try it again. 208.5. Boom. Times 16. That value. Then 73.4 times 14. Boom. Okay. Subtract that out. All right. So this should be. See, it was good that I checked. There you go. I am definitely, if you see the poster in my office, it says it could be the purpose of your life is only to serve as a warning to others. I am that kind of role model. What not to do. So that's not, this would be negative 2,308. And if you multiply 256.5 times 9, boom, you should get the same thing, and you do. It's actually, this could be a 9 instead of an 8. It's sort of questionable. I got 2,308.4 going in this direction. I got 2,308.5 going in that direction, so can't really decide. All right, so the same thing over here for our rods. We found that it was going in the positive direction at 259. And then we went up with the RAZ, and the RAZ was 102.3. And so that's going in the negative direction, so that's not going to be enough to make this colored much, but it's going to, well, I mean, actually I should make it a little bit wider than that. So this is 259.3, and then I'm going to have 102.6. Subtract from it. So we're left with 156.7. And then this is going to go downwards. So, ooh, wait. Oh yeah, I remember. So we have to go like that right there. I messed up already. So our CZ, recall, we found that it was actually going in the negative Z direction, right here. So I have to be careful there. So that's got to go up. So we're going to, and it was a value of 861. So that's a lot. 861.5. So we get right here the negative 704.8, which should match up with FBZ. So that confirms we got that right. And so now we can go, let's see, this is going to be up to here. And so 259.3 times 16 is our 4,149. Now we can add 156.7 to this. 156.7 times 14. 156.7, 14 times, add it, right? So now it's increasing, but the slope has changed. So that's going to go 6,343. It's going to go back down to 0 if we got it right. But let's check if we got it right. 704.8 times 9. 704.8 times 9. Boom. Yes, we get the identical thing. So we've confirmed our sum of the moments were correct. Yay! And there was much applause. Now what we want to do is find out where the maximum moment is going to be. So the moment at the thing we're calling A is going to be this combined with that. This is a mistake that gets made a lot. If they combine that one with that one, this is the same spot on the shaft as that. So 3,336 squared plus 4,149 squared. So 3,336 squared, 4,149 squared plus, and then square root the heck out of that, and we get 5,324 inch-pounds. You can already see this is going to be the worst one because that's already 6,000 right there. So now we're going to go M, and they decided to call this point C, which is a weird thing for them to do. And so we get 2,308 squared plus 6,343 squared, or 2,308 squared, 6,343 squared plus square root, and you got 6,750 inch-pounds, which is the max. All right, so now we get into the most recent thing that we were covering. We'll continue with that too. And we want to try to say, let's say, right, so let's go for stress. Now this is going to be the nominal stress in bending, and the nominal stress for torsion. So I would actually say this, the thing I'm going to have to do soon would almost kind of fit, and sometimes I will do it in the geometry section of this process. But let's say we'll put in that moment is going to be, I just covered it up, 6,750. The R is, the C, excuse me, is going to be the diameter, which is 1.25 divided by 2. Can't do that in my head. I is 1.9175. Mr. Lazy decided to do this for some reason. Remember our torque was 2,819. 1.25 divided by 2. And our J was 3,336 2.835. And, you know, I'm going to start writing that out that I'm divided by 1,000. I should. I feel guilty about it sometimes. Of all the things to be feel guilty about, that's what I chose. All right, so, ooh, that doesn't seem right. No, that does not seem right. That's too low. You know what? Maybe they fixed this problem. Maybe they made that shaft too small in previous editions. I just could have sworn this was the problem when it had ridiculously high stress. Interesting. Maybe I haven't done this problem since this edition. Because are you getting like really small mechanical?
2.64 for one and 0.55 for the other.
Yeah, that's not what I remember it being. I remember it being a crazy number. 2819. They must have fixed it. Well, okay, that's good news. Oh wow, this was really small. Did you say 0.459?
I think so, yeah. That's the small population there. At 1.459.
Huh, that's kind of boring. So let's see, stress concentration. For this right here. Well, I had said that what we're doing is we're going to say, like, let's just pretend that the gear and the, I don't know. Okay, so I'm going to pick a transition. I'm going to say that this thing is going from a 1-inch shaft, or no, there's a bigger shaft right here. So it's going to go from 1.25 to a 1.5-inch shaft. All right, so there's a change right here. So we're going to have a fillet in here of 1/16, which is 0.0625 inch. So looking up in our book, these two stress concentrations, it would be these two right here. It would be bending, and it would be torsion. And each of them have a D over D, and each of them have an R over D. So, and the D is based on the smaller D, right? So, looking at what I've just randomly chose, hopefully it appears on this chart, or close to it, is going to be big D over little d. 1.5 over 1.25. Can only hope that is a value that will be easily found. 1.2. It's not bad. And then the R over D, 0.0625 divided by 1.25. Ooh, 0.005. Oh. 0.05. Yes. Okay, so, yeah, okay, those aren't too, those look like they could be on there. The 1.2 is actually fairly fortunate, because if we go to this one, okay, look where it goes. Last time having a sharper pencil kind of helps. You can look up in here, and we have 1.1 and 1.5. So somewhere in between these two lines
but going to probably bias. It's not quite halfway, because halfway would be, the difference between those is 4, so, yeah, so 1.3 would be exactly halfway in between 1.1 and 1.5. And we have these two curves, and you can see that 0.05. So we're kind of, I would say, like right around there. What do you think? So a little bit below this line. And this is 1.8, and this is 2.2, so this must be 2.2. Excuse me, 2.0, sorry. And so 1.9 is halfway in between. What do you think about 1.95, or even give it a little bit of a nod, 1.96?
Sure.
You're getting like a little picky. It's tough, right? You will influence the result. So that was the KT. It was based on bending, 1.96. In fact, let's give it a little nod to our approximation by going the squiggly parentheses. And now we need the KTS by going this for the torsion. Gotta be careful to look at these really carefully. Gotta be careful to look at these really carefully. That's great project tip. 1.2, they have 1.2 over here. That's kind of nice of them. And we have ooh, look at that. That actually lands right the hell on it. It's hard to argue with that one, right? That's 1.6. It's gotta be 1.6. They said it's hard to argue. I could argue about it because I could argue about everything. Mr. Contrarian. I wrote something like that too. I am the contrarian. Oh, it's not very good, but it is a song. So we got sigma is going to be KT times sigma nominal. And so you're going to go 1.96 times R 2.200. 1.96, 2.2. So you have 4.312 KSI. And then tau is going to be the KTS times tau nominal, or 1.6 times the pathetic 0.494. 4594. And we still haven't made it over 1 KSI. And I'm way over time because I talked way too much about Larry Brown. But the remainder of this, what we would do is plot these out. We could put this on a, we'll assume it's tension, because when it's bending, it's tension and compression. It just depends on which side you're looking at. And it doesn't really matter what direction these arrows go. But you want to, I think it's a good idea to always write this thing out. You put it on here. And so as drawn here, on this face, this is counterclockwise. And this is clockwise. So clockwise goes to the top. I didn't do a great job with this button. So we would say that the center is going to be equal to 4.312 plus 0 divided by 2. So 2.156. And R is going to be equal to the square root. Now we have this length right there, which is what we just found, 2.156 squared, plus the tau, which is 0.7530. So we can square it and square it. Square it, square together. 2.156 and 2.278. Boom. You say principal stress is 4.434, and the other principal stress is going to be C minus R. It's going to be a small number. 2.278. 3.156. I subtracted the wrong one, but anyway, you'd have a negative 0.122. So not a whole lot. KSI, there's a 0 right there too. But what we really care about with the maximum shear stress theory is we would take this and we would take the yield strength divided by 2 and take the abs max, which is what this equals. Because it's going to be the same thing as this right here, right? Tau abs max. And Mr. Fussy Britches also wants to write this out here too. Of course, this is more circular. This is tremendously not the scale because that's an itty-bitty number. We weren't given the yield strength, but maybe we were going to go the other way and we want to pick out a material, but we're going to be okay because it's not a whole lot. We need to find out what the required design would be if we were to go and pick out what the strength would of a particular thing. But there's a problem all the way through. A real problem, real book. I kind of want to take a look at these right here from problem 383 and see if we got the right number. See. Because I have a sneaky suspicion we didn't. I might have did something wrong. And if I did something wrong, I want to know what it is that I did wrong. Curiosity. So let's see. We got ourselves a book. Books. Machine design. I still call it machine design. And Shigley 11th edition. From Blink. Guitaring has been disconnected for them. So you can go to my guitar room right now and it doesn't have the security camera. And what color is this? It was 80. How come it only goes to... Oh, there you go. It jumped. Motion sickness. Write all this down. Was this the results that we got for A&B? Yeah. Yep. So what did I do wrong with the stresses here? I must have calculated it wrong. What do you think? Maybe I must have done... This must be wrong. It's 1.25, right?
Your MC was around 32 times.
Okay, no, they use. Okay, so they're using a simplifying thing for the diet. Yeah, this is. I mean, let me just quick double check what I must have right from the very beginning, I did something wrong. Maybe I forgot to divide by 64. Is that correct? Oh, I was off by a tenth. Is that right? No, I'm off by a lot. Try 1.25. 1.25 is to hit the calculator on it. Really? Times pi, divide by 64. Yeah, this should have been 0.1984. And 2 times it should have been 0.02397. So this, boom, 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 boom. So you should have 6750, 1.25 times 2 divided. And if I had an excuse, right, but I think this calculator had got some kind of nasty something on it. Yeah, there you go. I got 21 point. Well, you can't write that. You can't see what you're writing this down. 21.26 KSI. And this is 2819. I'm not going to fix all the numbers. I just want to double check that we got everything right. All right, so that's 0.2397 divided. So I got like 7.35. 0 KSI. Yeah. All right. Oh wait, I think I got 35. What the hell did I do wrong again? I'm calculating something wrong, apparently. 7. I'm sorry. 6750. Maybe 1.25. And 0.19. Getting the same thing again. How's that possible? I don't know. Okay, can you calculate what they did? Is there any chance they have them calculator?
For the magnitude?
You know, for this right here. That is the correct equation, by the way. That's just a shortcut. Yeah, I get that. I just don't know what the hell is wrong with me. Why can't I get the same answer? Alright, well, let me stop the video here, because I don't want to get